Ever wondered how a 150-ton metal tube stays in the air? We're about to take you on a journey inside the brain of a jet airliner. You'll see how engines generate massive thrust, how wings create lift, and how pilots make split-second decisions using advanced technology. Welcome to Explained Universe. Today we're diving into how jet airliners work, from powerful engines to high-tech systems, uncovering what keeps planes soaring safely. Let's get started. Don't forget to subscribe. Now onto the cockpit of a modern jet airliner. As you settle into the virtual co-pilot seat, you'll notice an array of instruments and controls surrounding you. These sophisticated systems form the core of the aircraft's operation. We'll explore three primary components: the powerful engines that propel us forward, the intricate navigation systems that guide our path, and the complex communication networks that keep us connected with the ground. You're about to embark on a long-haul flight, but weather reports indicate potential turbulence ahead. How will the aircraft's systems respond to this challenge? As we prepare for takeoff, we'll examine how each of these critical systems works in tandem to ensure a safe and efficient journey, even in the face of adverse conditions. As our aircraft prepares to face the turbulence ahead, a more fundamental question arises. How does this massive machine even get off the ground? The secret lies in a delicate balance of forces, where the laws of physics are harnessed in ways that might surprise you. At the heart of every jet airliner are its engines, powerful marvels of engineering that generate the thrust needed for flight. These engines operate on a simple yet effective principle. They suck in large volumes of air through a front fan, compress it, mix it with fuel, and ignite the mixture. The resulting explosion creates a rush of hot air exiting the engine, propelling the aircraft forward. But thrust alone isn't enough to achieve flight. The real magic happens when this forward motion interacts with the carefully designed shape of the aircraft's wings. As the wing moves through the air, it causes a thin layer of air to stick to its surface. This layer pulls surrounding air with it, creating a faster airflow above the wing than below it. This difference in airflow speed leads to a pressure difference. The faster moving air above the wing creates an area of lower pressure, while the slower air below maintains higher pressure. It's this pressure difference that generates lift, the upward force that counteracts the aircraft's weight and allows it to fly. A common misconception is that air molecules above and below a wing meet at the trailing edge at the same time. In reality, the air above the wing travels faster, disrupting this supposed symmetry. The true mechanism of lift is more complex and relies on the overall pressure distribution around the wing. During takeoff, pilots must carefully manage both thrust and lift to get the aircraft airborne. They adjust engine power to maximum and manipulate control surfaces to optimize the wing shape for maximum lift. Two critical components in this process are the leading edge slats and trailing edge flaps. Leading edge slats extend outward and downward from the front of the wing, while trailing edge flaps lower and extend from the back. These devices effectively change the wing's shape, increasing its ability to generate lift at lower speeds. This is crucial during takeoff and landing when the aircraft needs maximum lift at relatively low speeds. As the aircraft accelerates down the runway, these high lift devices allow it to achieve flight at a lower speed than would be possible with a clean wing configuration. The extended slats and flaps create a steeper climb angle and reduce the risk of stalling, ensuring a safe ascent even in challenging conditions. The aircraft's ascent is just the beginning of its journey. Once at cruising altitude, it must navigate through a three-dimensional maze of air traffic and weather patterns. This requires a level of precision and coordination that would be impossible without the plane's hidden nervous system, a network of antennas and computers that keep it connected to the world below. At the heart of this system is an array of sophisticated antennas strategically placed across the aircraft's fuselage. These antennas serve multiple purposes, enabling radio communication, GPS positioning, collision avoidance, and air traffic surveillance. They form the backbone of the plane's constant connection with ground stations and other aircraft, ensuring safety and coordination throughout the flight. The navigation system integrates data from multiple sources to determine the aircraft's precise location. GPS satellites provide global positioning information, while inertial navigation systems use gyroscopes and accelerometers to track the plane's movements. Ground-based radio beacons offer additional reference points. This multi-layered approach allows pilots to know their exact position, even when flying over featureless oceans or through dense cloud cover. Communication systems play a crucial role in maintaining situational awareness. Pilots receive regular updates on weather conditions, air traffic, and potential hazards through their onboard communication systems. This constant flow of information allows for real-time decision-making and course adjustments when necessary. Consider a scenario where the aircraft encounters unexpected weather patterns. As the flight progresses, updated meteorological data is transmitted to the cockpit. The pilots analyze this information and determine that a course change is necessary to avoid turbulence. They input new coordinates into the flight management system, which then calculates the most efficient route to the destination while accounting for the weather deviation. This seamless integration of navigation and communication systems allows for smooth adaptations to changing conditions. The flight management system continuously updates the aircraft's flight plan, ensuring optimal fuel efficiency and adherence to air traffic control instructions. Redundancy is a key feature of these critical systems. Multiple backup systems are in place to ensure that if one system fails, others can take over, maintaining safety during flight. This multi-layered approach to navigation and communication provides pilots with reliable information even in the unlikely event of equipment malfunction. The aircraft is equipped with a vast array of antennas for radio communication, GPS, collision avoidance, and air traffic surveillance, ensuring a continuous connection with ground stations and other aircraft. This quote from aviation experts underscores the complexity and importance of these systems in modern aviation. As the flight progresses, these navigation and communication systems work tirelessly in the background, processing vast amounts of data to keep the aircraft on course and in constant contact with the ground. They form the nervous system of the plane, allowing it to respond to changes in its environment and maintain safe operations throughout the journey. As our aircraft cruises through the sky, it encounters an invisible challenge: turbulence. How does a massive airliner maintain stability when the air turns choppy? The answer lies in a complex interplay of sensors, systems, and structural engineering that works invisibly to keep passengers safe and comfortable. Modern aircraft are equipped with sophisticated sensors designed to detect changes in air pressure and wind speed. These sensors act as the plane's early warning system, alerting pilots to potential turbulence before it's felt in the cabin. This advanced notice allows the flight crew to take preemptive measures, such as adjusting altitude or course to minimize the impact of rough air. When turbulence does occur, the aircraft's autopilot system works in concert with flight control surfaces to maintain stability. Ailerons, elevators, and rudders automatically adjust to counteract sudden changes in airflow. This automated response happens faster than human reflexes, ensuring the aircraft remains level and on course even in challenging conditions. Inside the cabin, passengers might notice little more than a slight jostling. This is due in part to the aircraft's pressurization system, which maintains a comfortable internal environment despite rapid changes in outside air pressure. As the plane encounters turbulence, this system continuously adjusts to keep cabin pressure at a consistent level, typically around 14 psi, even when external pressure drops significantly at high altitudes. The structural integrity of modern aircraft plays a crucial role in weathering turbulence. Planes are constructed using carbon fiber reinforced materials and aluminum alloys, providing both strength and flexibility. This design allows the aircraft to absorb stress from turbulence without compromising safety. The wings in particular are engineered to flex, dissipating energy from air movements and reducing the impact felt inside the cabin. During periods of turbulence, the aircraft's flight control systems work tirelessly to counteract external forces. Ailerons on the wings adjust to prevent excessive rolling, while elevators on the tail maintain level flight and prevent pitching. These automated adjustments happen continuously, often imperceptibly to passengers, ensuring a smooth ride even in rough air. It's important to note that while turbulence can be uncomfortable, it poses little threat to modern aircraft. The systems and structures designed to handle turbulence are tested to withstand forces far greater than those typically encountered during flight. This means that even in severe turbulence, the aircraft remains well within its structural limits. The aviation industry continues to evolve, with emerging technologies pushing the boundaries of flight. New engine designs like Pratt & Whitney's Pure Power engine allow for slower fan speeds relative to the turbine, resulting in reduced fuel consumption and noise levels. Advanced materials, including carbon fiber reinforced composites and lightweight aluminum alloys, are increasingly used in aircraft construction, creating lighter airframes without compromising structural integrity. Automation in flight control systems is enhancing safety and efficiency, allowing for more precise handling of aircraft in various scenarios. The future of flight also looks towards sustainable aviation fuels, SAFs, that can significantly reduce carbon emissions. As automation increases, pilots will rely more on advanced cockpit technology, integrating real-time data for better decision-making. These innovations not only improve the efficiency and safety of air travel, but also showcase the continuous ingenuity in aviation technology, pushing the boundaries of what's possible in human flight. Thanks for watching Explained Universe. If you enjoyed discovering how jet airliners work, don't forget to like, subscribe, and hit the bell for more fascinating tech and engineering breakdowns. See you in the next video.